Welcome back. Having introduced nuclear fission reactors, in this lecture, we will contrast the behavior of thermal neutrons and hot and fast neutrons in the context of nuclear fission reactors. This behavior, fairly counterintuitive behavior of thermal neutrons, was one of the main reason uh, Enrico Fermi won his Nobel Prize in 1938. So amongst the different isotopes of uranium, U-235 is the most relevant for nuclear fission. So in a previous lecture, we had seen that one atom of U-235, the fission of one of the atom gives rise to 200 MeV of energy, and on an average 2.42 neutrons. That is, it generates more neutrons than it uses up. This is very important for sustaining nuclear fission reaction. Sometimes, even after absorbing a neutron, the de-excitation can occur via gamma emission. Okay, so this is not going to be useful for nuclear fission. So gamma-based de-excitation competes with nuclear fission. So to re-emphasize, when neutron of just thermal energy, that is at room temperature, so neutrons of energy 26 milli electron volts, when it is added to U-235, it goes to a higher energy state, and the higher energy state is good enough to cross the fission barrier for U-235. This is not the case for U-238. So the emphasis here is on U-235. Most importantly, and counterintuitively, the fission cross-section decreases with increase in energy of the neutron. We have seen a plot of this parameter, reaction cross-section. So what we are stressing is that when the energy of neutron increases, its velocity increases, and the cross-section to nuclear fission decreases. It has a 1/v relationship. So it is much more advantageous to have neutrons at room temperature. These are referred to as thermal neutrons. So what is plotted here is a nuclear neutron energy spectra. Here, U-235 fission is induced by 1 MeV neutron. What you see is that the fission generates a lot of neutrons at fairly high energies, right? Because a lot of energy is generated, and while most of the energy goes into the fragments of nuclear fission, these are fairly elements of fairly large Z. Much of the energy also goes into neutrons, and these neutrons have fairly high energy because their capacity to initiate nuclear fission is much less than the capacity of thermal neutrons to initiate nuclear fission. You really want to slow down the high energy neutrons. So as emphasized, with thermal neutrons, even natural uranium, that is, natural uranium consists not only of U-235, in fact, that's a very, very minor component. Most of natural uranium is U-238, which is not susceptible to fission with thermal neutrons. But when even in a mixture of U-235 and predominantly U-238, thermal neutrons is good enough to initiate nuclear fission. So because of the capacity of thermal neutrons to initiate fission, you want to have moderators. These are the components which slow down the high energy neutrons. So there is a momentum and energy transfer from high energy neutrons to certain substances. And these substances which slow down the fast neutrons are called moderators. If you just have high energy neutrons, such reactors are called fast reactors. Here, fast indicates the velocity of neutrons. So you have high kinetic energy neutrons present in this reactor because its capacity to generate nuclear fission is not that uh, high. You need to have greater concentration of U-235. So if you do not use moderators, you only have fast neutrons, but the trade-off here is that while you do not use moderators, the concentration of U-235 required in these reactors is much larger. So what are the options for moderators? Typically, one of the main constraint is that the moderator should only slow down the neutron. Okay, it should not absorb the neutron. This is quite a challenge because neutrons are neutral particles; they are chargeless. Therefore, it can easily be absorbed and penetrated. Okay, well, it can penetrate into many substances. So you do not want moderator to be absorbing neutrons. So the neutron absorption cross section for a moderator should be less. The main purpose of a moderator is to reduce the kinetic energy and not absorb neutrons. So atoms which are lighter do a better job of slowing down the neutrons. That is, the momentum transfer from the neutrons to the moderator is more efficient if the moderator is made up of light elements. So deuterium is a very good choice because its absorption cross section here, what we are showing here is a neutron absorption cross section of deuterium that is quite low. So deuterium is part of heavy water. Okay, so that's why heavy water is a good moderator because it can not only slow down the neutron, it will not also absorb neutrons. Graphite is also a very good choice because it's a solid. The capacity it is easier to handle compared to liquid. Its neutron absorption cross section is also less. Beryllium is another solid whose neutron absorption cross section is more than these two elements, but still is a good moderator. In fact, in the early days, this was used, as you will see in one of the later lectures in this series. So if normal water is used, its neutron absorption cross section is greater, but it's more effective in terms of momentum transfer and kinetic energy transfer. So because you would be absorbing more of the neutrons, the U-235 that is to be used is more enriched. So you need more concentrated mixture wherein there is greater amount of U-235. So if you have heavy water, you may use lesser amount of U-235. So most of engineering is about trade-off. When you gain some, you lose some part. So you have to optimize depending upon the different scenarios. So what we show here is two kinds of reactors. One is a light water reactor. Because it's a very good moderator, you would see that even at low neutron energies, there is a lot of neutrons that is present. Okay? As opposed to this, if you have a fast breeder reaction, we'll clarify what's a breeder reaction at a later stage. But right now, the emphasis is on fast. That is, most of the neutrons that are present have fairly high kinetic energy. Okay, so here you don't use a moderator, so that decreases the complexity, but you need more enriched fuel when you have a fast reactor. So what we show here is the reaction cross section when thermal neutron initiates nuclear fission in different systems and contrast that with fast neutron initiating fission. So here, three different fissionable atoms are shown. U-233, which is also not significant, but U-235 is the main fuel, and plutonium is also becoming increasingly important. So what you see here is for thermal neutrons, the reaction cross section for fission is much more than reaction cross section for neutron capture. So most of the neutrons that collide with the nuclei results in fission, and not much of the neutron gets just captured without generating fission. So as opposed to that, when you have fast neutrons, you have much lesser reaction cross section. So what you have to contrast is this row against this row. Okay, so here the kinetic energy of neutrons is rather high, 1.5 MeV. So here the kinetic energy is of the order of kT, 26 MeV. I mean, here we are talking about 26 milli electron volts. Okay, that's what you mean by thermal neutrons. So reaction cross section for fission is rather high compared to reaction cross section here. For fast neutrons, the cross section for capture and not initiating fission is low, but so is the reaction cross section for fission. So it is not really advantageous to use fast neutrons. The number of neutrons per fission, okay, is not very different between the two scenarios. You also undertake what is called a neutron balance. Supposing if there are 100 fission events, 259 neutrons are generated. You want to account where do these 259 neutrons go? Because there are a lot of other components in the reactor, and because neutron is neutral, it can easily penetrate. Much or quite a bit of neutron is absorbed in supporting material, the structural materials, as well as in fission products. Okay, so these are called activated products, but do not give rise to energy or any other useful products. Neutron, when it gets absorbed by these elements, let's say plutonium, it absorbs 27 and so on. This produce higher actinides, okay, as well as from here you may generate plutonium, but you are not going to get energy. Okay, so the neutrons which get absorbed in this proportion, okay, that is out of 259, if this much is getting absorbed here, these neutrons are the ones that are going to give rise to energy. Okay, so that's important to note. Okay, so where do you get 259? If you add all these neutrons up, you will get 259 neutrons. So this is what is called neutron balance. So what we are contrasting is the behavior of thermal neutrons versus fast neutrons. In this section, you are showing the behavior of fast. So if you have a light water reactor, light water is a very good moderator. You only have thermal neutrons. In a fast reactor, you do not have a moderator. Therefore, the utilization of neutrons is different in the case of light water and a fast reactor. So you can look at the numbers, okay, and see the differences. So in the next lecture, we will look at the different options available in terms of nuclear fuel. Thank you.